Welcome to Tech with Kaushik. This is set 7 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 7. Next up is question number 108. We're working with S3 access denied from EC2 here. Here's the scenario. An automated reporting application running on an Amazon EC2 instance requires access to download configuration files from a private Amazon S3 bucket. The bucket is located in the same AWS account. When the application attempts to execute an S3 GetObject API call using the AWS CLI, it immediately receives an access denied HTTP 403 error. Which of the following issues could be the root cause of this access denied error? Choose 2. Select all answers that apply. Review the options. Choice A. The bucket uses default server-side encryption with Amazon S3 managed keys, SSES3, and the EC2 instance role has no AWS KMS permissions. Choice B. The requested configuration object has been transitioned to the S3 Glacier Flexible Retrieval Storage class. Choice C. S3 object versioning has been enabled on the bucket, and the application did not specify a version ID in its request. Choice D. The IAM instance profile attached to the EC2 instance does not include the S3 GetObject permission for the target object ARN. Choice E. An explicit deny statement in the S3 bucket policy is blocking access from the EC2 instance's IAM role or VPC endpoint. The required selections are option D. The IAM instance profile attached to the EC2 instance does not include the S3 GetObject permission for the target object ARN, and option E. An explicit deny statement in the S3 bucket policy is blocking access from the EC2 instance's IAM role or VPC endpoint. Let's look at the reasoning. An S3 GetObject request can return access denied when the caller lacks S3 GetObject for the object, or when an explicit deny in an identity policy, bucket policy, VPC endpoint policy, or other applicable policy overrides an allow. Therefore, the missing instance role permission and the explicit bucket policy deny are both direct root causes. The other choices do not work because A. SSES3 uses Amazon S3 managed keys and does not require the caller to have AWS KMS permissions, so absence of KMS permissions alone does not cause this GetObject access denied. B. An object in S3 Glacier Flexible Retrieval that has not been restored produces an invalid object state response rather than the access denied authorization error described in the scenario. C. For a normal GetObject request without a version ID, S3 returns the current version. Enabling versioning does not itself require the caller to specify a version ID. The main takeaway is for S3 403 troubleshooting. Distinguish authorization failures from storage state errors, and remember that SSEKMS, unlike SSES3, can add a KMS decrypt requirement. Question number 109. A company runs a distributed in-memory data store on a fleet of Amazon EC2 instances managed by an auto-scaling group. Whenever the cluster scales out or scales in, all instances currently in the cluster must be reconfigured. The /etc/cluster/nodes.config file on every active instance must contain the current private IP addresses of all active cluster members, and the cluster service must then be restarted. A DevOps engineer needs to automate this reconfiguration process whenever an instance is successfully added to or removed from the auto-scaling group. Which solution will meet these requirements with the least manual intervention? Option A. Configure an Amazon EventBridge rule to match the EC2 instance launch successful and EC2 instance terminate successful events from Amazon EC2 autoscaling. Target an AWS Lambda function that retrieves the current auto-scaling group instance IP addresses and invokes AWS Systems Manager run command to update the configuration file and restart the service on the managed instances. Option B. Store the nodes.config file in an AWS code commit repository. Configure an AWS code deploy deployment group targeting the cluster's EC2 tags. Trigger a deployment every time a node is added to commit the new IP address and deploy the file to the fleet. Option C. Store the nodes.config file in an Amazon S3 bucket. Configure a cron job on all EC2 instances to download the file every minute. Use a process manager to restart the service when the file changes. Update the S3 object by using an EC2 user data script whenever a new instance launches. Option D. Create an EC2 user data script that queries the EC2 API for all instances in the cluster security group. Configure the script to update the local /etc/cluster/nodes.config file and restart the service whenever a new instance boots. Go with option A. Configure an Amazon Event Bridge rule to match the EC2 instance launch successful and EC2 instance terminate successful events from Amazon EC2 autoscaling. Target an AWS Lambda function that retrieves the current auto-scaling group instance IP addresses and invokes AWS Systems Manager Run command to update the configuration file and restart the service on the managed instances. This works because Amazon EC2 autoscaling publishes successful instance launch and termination events to Amazon Event Bridge. Event Bridge can invoke AWS Lambda, which can determine the current auto-scaling group membership and use AWS Systems Manager Run command to apply the updated configuration and restart the service across the managed EC2 instances. This event-driven design handles both scale-out and scale-in and does not require polling or manual fleet reconfiguration. The remaining options can be eliminated because AWS Code Deploy can deploy application revisions. But this design still requires a separate mechanism to discover the current cluster membership, update the repository, and initiate a deployment after every scale event. C. Polling Amazon S3 every minute adds delay and unnecessary recurring work. In addition, a user data script that runs when a new instance launches does not reliably update the shared configuration after a scale-in event. D. EC2 user data runs on the newly launched instance and does not reconfigure the existing cluster members. It also does not address instance termination events. Here's a useful exam tip. 4 fleet-wide configuration changes triggered by auto-scaling membership changes. Use Event Bridge for the scaling event, Lambda for orchestration, and Systems Manager for fleet-wide execution. Next, question number 110. We're moving on to S3 put object MD5 validation. Scenario. A DevOps engineer is writing a Python migration script to move legacy on-premises data to a general-purpose Amazon S3 bucket that uses SSES3. Each file is uploaded with a single put object request. Multi-part upload is not used. Because the data contains sensitive financial records, the script deletes each original file immediately after a verified upload. A reviewer requires strict MD5 integrity verification before the local file is deleted. Which methods can the engineer implement to strictly verify the data integrity, MD5 checksum, of the object before allowing the script to delete the local file? Choose 2. Choose every option that satisfies the requirement. Choices. Option A. Calculate the file MD5 digest locally and send the base 64 encoded digest in the content MD5 header of put object. If S3 calculates a different MD5 digest, S3 rejects the upload. Option B. After a successful single-part SSES3 put object, normalize the returned E tag and compare it with the locally calculated hexadecimal MD5 digest before deleting the local file. Option C. Pass the locally calculated MD5 hash into the exams metachecksum metadata parameter. After the upload completes, issue a head object request to verify the metadata was saved. Option D. Append the locally calculated MD5 hash as a URL query string parameter when formulating the put object endpoint URL. E. Check the put object response payload for the version ID attribute and mathematically compare it against the local MD5 digest. The correct answers are option A. Calculate the file MD5 digest locally and send the base 64 encoded digest in the content MD5 header of put object. If S3 calculates a different MD5 digest, S3 rejects the upload and option B. After a successful single-part SSES3 put object, normalize the returned E tag and compare it with the locally calculated hexadecimal MD5 digest before deleting the local file. Here's why. Content. MD5 provides end-to-end request validation for put object. S3 calculates the received payload MD5 and rejects the request if it does not match the supplied base 64 encoded value. Under the stated single-part SSES3 conditions, the put object E tag is the object MD5 digest, So comparing it with the local MD5 provides an additional post-upload check before deleting the source file. C. Storing the checksum as an arbitrary metadata parameter, exams metachecksum, merely saves the string alongside the object. S3 performs no mathematical validation against the actual file contents, meaning a corrupted file would still upload successfully. D. Appending the checksum as a URL query string is syntactically invalid for the PutObject API and does not trigger any built-in S3 data integrity validation mechanisms. E. The version ID is a randomly generated alphanumeric string used by S3 versioning to uniquely identify object iterations. It has no mathematical relationship to the object's MD5 checksum or data integrity. Exam tip. Content. MD5 is an explicit PutObject integrity check. Treat eTag as MD5 only when the upload and encryption mode make that relationship valid. Question number 111. Let's go. A company publishes a public RESTful API using Amazon API Gateway. The deployments are orchestrated fully through an AWS code pipeline. To assist downstream developers, the company maintains a JavaScript SDK that must be regenerated whenever the API schema changes. Currently, a developer manually exports the SDK from the API Gateway console, uploads it to a specific Amazon S3 bucket, and manually invalidates an Amazon CloudFront distribution that serves the SDK to end users. A DevOps engineer needs to completely automate this post-deployment workflow. Which solution achieves this requirement with the least manual intervention? Options. Option A. Create an Amazon Event Bridge rule that listens for create deployment API events from the AWS Gateway namespace. Route the event to an AWS Lambda function that downloads the SDK, uploads it to S3, and calls the S3 invalidation API. Option B. Add an AWS Lambda invoke action to code pipeline immediately after the API Gateway deployment stage. The Lambda function calls the API Gateway getSDK operation for the JavaScript SDK, uploads the generated SDK to the S3 bucket, and calls CloudFront create invalidation. Option C. Add a native code pipeline, export SDK, integration action immediately following the deployment stage, mapping the output directly to the S3 bucket. Add a subsequent code pipeline action to invalidate the S3 cache path. Option D. Create an Amazon Event Bridge rule that listens for update stage API events from the AWS Gateway namespace. Route the event to an AWS Lambda function that downloads the SDK, uploads it to S3, and calls the CloudFront invalidation API. In this case, choose option B. Add an AWS Lambda invoke action to code pipeline immediately after the API Gateway deployment stage. The Lambda function calls the API Gateway getSDK operation for the JavaScript SDK, uploads the generated SDK to the S3 bucket, and calls CloudFront create invalidation. The main reason is code pipeline can invoke Lambda as a pipeline action, so the SDK generation can remain in the same deterministic deployment workflow. The Lambda function can call API Gateway getSDK to generate the requested SDK, store the result in S3, and call CloudFront create invalidation so clients receive the new content. Pipeline failure handling then covers the post-deployment automation as well. Let's quickly check the incorrect choices. A. The option refers to an S3 invalidation API, which does not exist. Cache invalidation is a CloudFront operation, and an external event bridge workflow is also less tightly coupled to the deployment pipeline. C. Code pipeline has no native export SDK action that directly emits an API Gateway SDK to S3. Custom logic, such as a Lambda action, is required. D. An event bridge triggered Lambda could be built, but it decouples the required post-deployment work from pipeline success and is less operationally direct than a Lambda invoke action in the existing pipeline. Keep this point in mind for the exam. When a deployment requires an API-specific post step that code pipeline does not provide natively, invoke Lambda inside the pipeline and use the service API directly. Question number 112. Scenario. A serverless microservice utilizes an AWS Lambda function exposed via an API Gateway endpoint. The development team uses AWS Code Deploy to perform controlled traffic shifting deployments for new versions of the function. Recently, the team noticed that the API returns intermittent 500 errors for several seconds immediately after Code Deploy completes a traffic shift. Investigation reveals that the new Lambda version relies on a database schema migration that has not fully finished executing by the time the new Lambda version starts receiving production traffic. How can the DevOps engineer modify the code deploy configuration to guarantee the database is fully ready before any production traffic reaches the newly deployed Lambda version? Option A. Implement a validate service lifecycle hook in the AppSpec file that inspects inbound HTTP requests and drops them if the database connection fails. Option B. Implement a before-install lifecycle hook in the AppSpec file that executes a script to pull the database and block the deployment entirely until the schema migration completes. Option C. Add a before-allow traffic hook to the AppSpec file that invokes a validation Lambda function. The function verifies the database schema and calls code deploy, put lifecycle event hook execution status, with succeeded only when the schema is ready. Option D. Implement an after-allow traffic lifecycle hook in the AppSpec file to temporarily queue incoming API gateway requests while the database finalizes its schema migration. The best choice is option C. Add a before-allow traffic hook to the AppSpec file that invokes a validation Lambda function. The function verifies the database schema and calls code deploy, put lifecycle event hook execution status, with succeeded only when the schema is ready. This is the best choice because for an AWS Lambda deployment, code deploy supports before-allow traffic and after-allow traffic validation hooks. A before-allow traffic validation Lambda runs before production traffic is shifted. The function must report the hook result to code deploy with put lifecycle event hook execution status. Only a succeeded result allows the deployment to continue, so the database dependency can be verified before users reach the new function version. Here's why the alternatives are not suitable. A. The validate service lifecycle hook is specific to EC2/on-premises deployments, not AWS Lambda deployments. Lambda deployments only support before-allow traffic and after-allow traffic. B. The before-install lifecycle hook is specific to EC2/on-premises and Amazon ECS deployments. It is not supported in AWS Lambda deployments. D. The after-allow traffic lifecycle hook executes after code deploy has shifted the traffic to the new function version. If the database is unready, the new function is already receiving live requests, resulting in the 500 errors the team is trying to prevent. For Lambda traffic shifting deployments, use before-allow traffic to validate dependencies and report the hook result with put lifecycle event hook execution status. Question number 113. Let's go. This is a harder question, so check every requirement carefully. Scenario. A security team uses the AWS config managed rule restricted SSH to detect security groups that permit unrestricted SSH access. Whenever this specific rule changes a resource to NON_compliant, the team must receive an Amazon SNS alert. The message must be formatted for operators and include the config rule name, affected resource type, and affected resource ID without running custom compute. What is the most operationally efficient way to generate this customized notification? Choices. Option A. Configure AWS config to stream all evaluation results to the SNS topic. Apply an SNS filter policy matching the string NON_compliant to restrict which messages are forwarded to the subscribers. Option B. Create an Amazon event bridge rule that matches AWS config rules compliance change events where config rule name is restricted SSH and new evaluation result, the compliance type, is NON_compliant. Use an event bridge input transformer to extract the rule name, resource type, and resource ID and format the message before sending it to the SNS topic. Option C. Create an Amazon event bridge rule that filters for AWS config evaluation events where the compliance status is NON_compliant. Target the rule to an AWS Systems Manager run command document that formats the message and dispatches it to the SNS topic. Option D. Create an Amazon event bridge rule that filters for AWS config evaluation events across all managed rules. Apply an event bridge input transformer configured specifically for the restricted SSH payload. Target the transformed output directly to the SNS topic. The right response is option B. Create an Amazon event bridge rule that matches AWS config rules compliance change events where config rule name is restricted SSH and new evaluation result, the compliance type, is NON_compliant. Use an event bridge input transformer to extract the rule name, resource type, and resource ID and format the message before sending it to the SNS topic. AWS config emits compliance change events to event bridge that include the config rule name and the evaluated resource type and resource ID. An event bridge rule can filter for restricted SSH and NON_compliant, and an input transformer can extract those existing event fields and format a concise message before delivery to SNS without Lambda. Now let's rule out the other options. A. Direct config to SNS delivery does not provide the same selective event bridge filtering and operator-oriented message transformation required by the scenario. C. Systems Manager Run command executes commands on managed nodes and is unrelated to transforming AWS config event payloads. D. A broad rule for every NON_compliant evaluation would send unrelated config violations and would not satisfy the requirement to notify only for restricted SSH. A helpful shortcut is this. Event bridge input transformer can reformat fields that already exist in an event, use Lambda or another lookup step when the desired message requires external enrichment. Here comes question number 114. Here's what is happening. A company strictly uses AWS CloudFormation to manage its infrastructure, explicitly prohibiting out-of-band manual changes. A DevOps engineer attempts to update a critical application stack using the AWS CLI. The stack update fails because an underlying dependency limit is reached, prompting CloudFormation to automatically initiate a rollback. During the rollback, a specific auto-scaling group resource fails to revert to its previous state, leaving the entire stack frozen in the update_rollback_failed status. The engineer determines the root cause, requests the necessary quota increase, and confirms the account limit has been raised. What is the correct sequence of actions to return the CloudFormation stack to a healthy state? Option A. Manually delete the problematic auto-scaling group from the EC2 console. Execute the AWS CloudFormation rollback stack CLI command to force CloudFormation to recreate it. Option B. Ensure the CloudFormation execution IAM role has the necessary permissions. Execute the AWS CloudFormation continue update rollback CLI command, optionally specifying the auto-scaling group to skip if necessary. Option C. Verify the quota increase is active. Execute the AWS CloudFormation cancel update stack CLI command to abort the failed rollback process. Option D. Update the VPC subnet mappings associated with the application's load balancer. Execute the AWS CloudFormation update stack set CLI command to push the new configuration. The answer here is option B. Ensure the CloudFormation execution IAM role has the necessary permissions. Execute the AWS CloudFormation continue update rollback CLI command, optionally specifying the auto-scaling group to skip if necessary. Let's look at the reasoning. When a CloudFormation stack encounters a critical error during an automatic rollback, it enters the update_rollback_failed state and pauses all operations. This often occurs because a resource cannot be reverted, either due to manual out-of-band modifications or underlying account quota limits. Once the engineer identifies and resolves the external issue, in this case, securing a quota limit increase, the CloudFormation stack must be explicitly instructed to resume its rollback process. The only valid AWS CLI command to execute this is AWS CloudFormation continue update rollback. If the specific resource remains stubbornly broken despite the limit increase, the engineer can use the resources to skip flag to instruct CloudFormation to ignore the ASG, mark it as successfully rolled back, and proceed with the rest of the stack. The other choices do not work because A. There is no rollback stack command available for a stack in the update_rollback_failed state. Furthermore, manually deleting resources out of band is explicitly prohibited by the company's policies and risks worsening the configuration drift. C. The cancel update stack command is only valid when a stack is actively in the update_progress state. Once a stack has failed and entered a rollback state, it cannot be canceled. It must be resolved via continuation or deletion. D. Updating VPC subnet mappings via update stack set is completely irrelevant to an auto-scaling group limit issue and is the wrong API command. You cannot initiate a new stack update while a stack is stuck in a failed rollback state. The main takeaway is if a CloudFormation stack is trapped in the update_rollback_failed state, you must resolve the external conflict manually and then issue the continue update rollback operation to unstick it. Next, question number 115. A DevOps team has deployed a fleet of Amazon EC2 instances serving a custom application. The team needs to implement a centralized logging architecture that allows them to interactively query both the application's internal OS-level logs and the AWS account's administrative API activity using a single integrated interface. Which architecture will meet these requirements with the least operational overhead? Options. Option A. Configure the unified Amazon CloudWatch agent on the EC2 instances to stream application logs directly to Amazon S3. Configure AWS CloudTrail to deliver API activity logs to Amazon S3. Use Amazon Athena to query both datasets. Option B. Configure the unified Amazon CloudWatch agent on the EC2 instances to stream application logs to Amazon Kinesis. Configure AWS CloudTrail to deliver API activity logs to Amazon Kinesis. Route the Kinesis streams into Amazon Redshift for querying. Option C. Configure the unified Amazon CloudWatch agent on the EC2 instances to stream application logs to Amazon CloudWatch logs. Configure AWS CloudTrail to deliver API activity logs to Amazon CloudWatch logs. Use CloudWatch logs insights to query both datasets. Option D. Configure the unified Amazon CloudWatch agent on the EC2 instances to stream application logs to Amazon CloudWatch logs. Configure AWS CloudTrail to deliver API activity logs directly to Amazon S3. Use the CloudWatch console to query both datasets seamlessly. The best choice is Option C. Configure the unified Amazon CloudWatch agent on the EC2 instances to stream application logs to Amazon CloudWatch logs. Configure AWS CloudTrail to deliver API activity logs to Amazon CloudWatch logs. Use CloudWatch logs insights to query both datasets. This works because Amazon CloudWatch logs serves as a highly scalable, centralized repository for both infrastructure and application logs. The unified Amazon CloudWatch agent installed on EC2 instances can tail local OS and application logs and stream them natively into specific CloudWatch log groups. Similarly, AWS CloudTrail includes a native configuration option to forward all account API activity directly into a CloudWatch log group. Once both datasets are centralized within CloudWatch, engineers can use CloudWatch Logs Insights, a purpose-built interactive query engine, to seamlessly search, analyze, and aggregate data across multiple log groups without provisioning any external analytics infrastructure. This fully managed approach represents the lowest operational overhead. The remaining options can be eliminated because A. While AWS CloudTrail delivers natively to Amazon S3, the CloudWatch agent cannot stream application logs directly to S3. It must stream to CloudWatch logs first or rely on Kinesis Data Firehose. Setting up Firehose and Athena introduces additional infrastructure complexity compared to the native CloudWatch Logs Insights. B. Streaming logs through Amazon Kinesis into Amazon Redshift represents a complex, high-overhead data warehousing architecture. It requires provisioning clusters, managing schemas, and maintaining data pipelines, which violates the requirement for low operational overhead. D. AWS CloudTrail delivers to S3 natively, but the standard CloudWatch console interface is not designed to interactively query raw S3 bucket objects. You would need Amazon Athena to query the S3 data, requiring two separate interfaces, CloudWatch for EC2, Athena for S3. Here's a useful exam tip. CloudWatch Logs Insights provides the lowest overhead native interface for querying centralized application logs via CW Agent and AWS API activity via CloudTrail integration. Question number 116. Consider this situation. A security team wants to enhance the visibility into a fleet of Amazon EC2 instances. The team has two distinct requirements. They must be alerted if any known software vulnerabilities, CVs, are discovered on the operating systems, and they must maintain a centralized, searchable audit trail of all interactive user login activities occurring on those instances. Which combination of AWS services and agents will satisfy both requirements? The choices are: Choice A. Use Amazon Inspector to continuously scan the instances for software vulnerabilities and route new inspector findings through Amazon Event Bridge to an Amazon SNS topic. Install the unified Amazon CloudWatch agent on the instances to send OS authentication logs to Amazon CloudWatch logs. Choice B. Utilize AWS Systems Manager Patch Manager to scan the instances for vulnerabilities. Install the Amazon Kinesis agent on the instances to stream the OS authentication logs directly into an Amazon S3 bucket. Choice C. Utilize AWS Systems Manager Inventory to detect software vulnerabilities. Install the AWS Systems Manager agent on the instances to capture OS authentication logs and forward them to AWS CloudTrail. Choice D. Configure Amazon CloudWatch anomaly detection to identify anomalous software vulnerabilities. Install the AWS config daemon on the instances to capture OS authentication logs and view them in the AWS config console. Go with option A. Use Amazon Inspector to continuously scan the instances for software vulnerabilities and route new inspector findings through Amazon Event Bridge to an Amazon S&S topic. Install the unified Amazon CloudWatch agent on the instances to send OS authentication logs to Amazon CloudWatch logs. Here's why. Amazon Inspector continuously assesses supported EC2 workloads for software vulnerabilities and publishes findings that can be routed through Event Bridge for automated S&S notification. The unified CloudWatch agent can tail operating system authentication logs and send them to CloudWatch logs, providing the centralized searchable login audit trail required by the scenario. B. AWS Systems Manager Patch Manager is used to orchestrate the application of patches, not primarily to act as a vulnerability scanning and alerting engine. Additionally, the Amazon Kinesis agent is designed for streaming high-throughput application data, like clickstreams, and is unnecessary overhead compared to the standard CloudWatch agent for basic system logs. C. AWS Systems Manager Inventory gathers metadata about instance configurations and software installed. It does not scan against CVE databases to report vulnerabilities. Furthermore, AWS CloudTrail only records AWS API calls. It cannot accept or store OS-level authentication logs from an EC2 instance. D. Amazon CloudWatch anomaly detection applies statistical machine learning models to numerical metrics, like CPU spikes. It cannot detect software CVEs. Furthermore, the AWS config daemon evaluates AWS resource configurations, not OS-level login logs. Exam tip. Use Amazon Inspector for EC2 vulnerability findings and EventBridge/S&S for alerts. Use the CloudWatch agent and CloudWatch logs for searchable OS-level login auditing. Now for question number 117. The focus now shifts to ASG failed launch alert. A heavily utilized application relies on an Amazon EC2 auto-scaling group to dynamically scale compute capacity. Recently, an underlying configuration error in the launch template prevented the auto-scaling group from successfully provisioning new EC2 instances during a traffic spike. The capacity shortage degraded application performance for several hours before the operations team discovered the issue manually. The team needs to implement an automated email notification system that alerts them immediately whenever a scaling action fails to launch an instance. What is the most direct and natively integrated way to configure this notification? Here are the options. Option A. Attach a lifecycle hook to the auto-scaling group that invokes an AWS Lambda function. Configure the Lambda function to check instance health and send an email if the instance is impaired. Option B. Create a custom Amazon CloudWatch alarm designed to invoke an AWS Lambda function whenever CloudWatch records a failed attach instance's API call in AWS CloudTrail. Option C. Configure the auto-scaling group's built-in event notifications to publish a message directly to an Amazon S&S topic whenever the auto-scaling EC2_instance_launch_error event occurs. Option D. Create an Amazon CloudWatch status check alarm targeting the EC2 instances in the auto-scaling group, configured to publish to an Amazon S&S topic if a status check failed metric spikes. In this case, choose option C. Configure the auto-scaling group's built-in event notifications to publish a message directly to an Amazon S&S topic whenever the auto-scaling EC2_instance_launch_error event occurs. The main reason is Amazon EC2 auto-scaling includes a highly reliable, built-in event notification capability. You can configure an auto-scaling group to natively publish messages directly to an Amazon S&S topic whenever specific scaling lifecycle events occur. To satisfy the requirement of alerting the team when an instance fails to boot, due to configuration errors or capacity limits. The engineer simply needs to select the auto-scaling EC2_instance_launch_error event type. This native integration requires no custom code, metrics, or alarms, making it the most direct and lowest overhead solution possible. Let's quickly check the incorrect choices. A lifecycle hook pauses an instance as it transitions states, for example, pending, wait. If the instance completely fails to launch due to a launch template error or AWS capacity issue, it never reaches a lifecycle transition state, meaning the Lambda function would never be invoked. B, relying on CloudTrail to capture failed API calls and trigger CloudWatch alarms to invoke Lambda is a complex, asynchronous workaround that reinvents the native functionality already built into the auto-scaling service. D, EC2 status checks, system or instance, evaluate the health of an instance that is already running. If the auto-scaling group fails to launch the instance entirely, no EC2 instance is created, and therefore no status check metric is ever generated or failed. Keep this point in mind for the exam. EC2 auto-scaling groups have native SNS event notifications. Use them to monitor fundamental lifecycle events like EC2_instance_launch and EC2_instance_launch_error without writing custom CloudWatch alarms. Question number 118. A cloud architect has designed a multi-account hub-and-spoke network topology using AWS Transit Gateway. All outbound internet traffic from the spoke accounts is routed through a central network operations account. In this central account, a third-party firewall appliance inspects the traffic before it exits via an internet gateway. The firewall appliance streams its syslog output to Amazon CloudWatch logs. The syslog messages include severity tags such as critical, high, medium, low, and info. The security engineering team requires an immediate alert whenever a log entry containing the critical severity tag is ingested. How can the DevOps engineer implement this alert using native AWS services? Options. Option A. Enable Amazon Guard Duty in the network operations account and configure it to ingest the transit gateway flow logs. Create an Amazon Event Bridge rule that triggers on Guard Duty findings of high severity, routing the alert to an Amazon SNS topic. Option B. Create a CloudWatch metric filter on the firewall log group that searches for the exact string pattern critical. Extract this occurrence into a custom CloudWatch metric. Define a CloudWatch alarm against this custom metric that publishes to an Amazon SNS topic when the threshold is breached. Option C. Deploy an Amazon CloudWatch synthetics canary to continuously ping the firewall appliance's health check port. Configure the canary to publish a message to an Amazon SNS topic if the health check responds with a critical state payload. Option D. Utilize AWS Firewall Manager to enforce centralized logging policies across all accounts. Create an Amazon Event Bridge rule targeting Firewall Manager events flagged as critical, routing the output to an Amazon SNS topic. The right response is option B. Create a CloudWatch metric filter on the firewall log group that searches for the exact string pattern critical. Extract this occurrence into a custom CloudWatch metric. Define a CloudWatch alarm against this custom metric that publishes to an Amazon SNS topic when the threshold is breached. This is the best choice because when a third-party appliance streams unstructured or semi-structured text logs into Amazon CloudWatch logs, the most efficient way to generate alerts based on specific log content is by using a CloudWatch logs metric filter. The metric filter continuously scans the incoming log stream for a specified string pattern, in this case, critical. Every time it finds a match, it increments a custom numerical metric in CloudWatch. The DevOps engineer can then create a standard CloudWatch alarm monitoring this custom metric. When the metric exceeds a value of 0, the alarm triggers and dispatches a notification natively to an Amazon SNS topic, alerting the security team in near real time. Here's why the alternatives are not suitable. A. Amazon Guard Duty is a managed threat detection service that analyzes VPC flow logs, DNS logs, and CloudTrail events. It does not parse or analyze custom application syslog output from third-party firewall appliances. C. Amazon CloudWatch synthetics canaries are headless browser scripts used to monitor endpoint latency and UI behavior. A canary cannot monitor or parse incoming syslog streams in a CloudWatch log group. D. AWS Firewall Manager is a security management service that centralizes rules for AWS WAF, AWS Shield, and AWS Network Firewall. It does not ingest, analyze, or generate alerts from third-party firewall syslog messages. To generate alerts from specific text patterns inside an incoming CloudWatch log stream, always use a CloudWatch logs metric filter paired with a CloudWatch alarm. Question number 119. A DevOps engineer is using an AWS CloudFormation template to automate the provisioning of a complex Active Directory environment. The template uses a CloudFormation custom resource backed by an AWS Lambda function to execute a proprietary API call that provisions an AD connector. When the stack is deployed, the Lambda function successfully executes and provisions the AD connector resource. However, the CloudFormation stack hangs in the create__progress state for the custom resource and eventually fails due to a timeout. What is the most likely reason CloudFormation fails to transition the resource to create_complete? Here are the options. Option A. The IAM execution role attached to the Lambda function lacks the DS connect directory permission required to interact with the AWS account. Option B. The Lambda function completes its execution successfully, but fails to send an appropriately formatted JSON response back to the pre-signed Amazon S3 URL provided in the event payload. Option C. The IAM execution role attached to the Lambda function is missing the CloudFormation update stack permission required to signal completion to the CloudFormation stack ARN. Option D. The Lambda function's internal application code executes successfully, but the runtime environment fails to exit cleanly with a zero status code. The answer here is option B. The Lambda function completes its execution successfully, but fails to send an appropriately formatted JSON response back to the pre-signed Amazon S3 URL provided in the event payload. AWS CloudFormation custom resources delegate provisioning logic to external endpoints, most commonly AWS Lambda functions. When CloudFormation invokes the Lambda function, it includes a uniquely generated, pre-signed Amazon S3 URL in the event payload response URL. For CloudFormation to transition a custom resource from create__progress to create_complete or failed, the Lambda function must explicitly execute an HTTP put request sending a specifically formatted JSON response object to that S3 URL. If the Lambda code executes its internal logic perfectly and exits, but neglects to send this HTTP callback payload, CloudFormation remains unaware of the success. It will hang in the create__progress state until its internal timer expires, typically 1 hour, after which it fails the stack. Now let's rule out the other options. A. If the IAM execution role lacked the DS connect directory permission, the Lambda function's internal API call would fail, throwing an access denied error in the Lambda execution logs. Assuming proper error handling, the Lambda should report a failure back to CloudFormation. If it lacked the permission and lacked error handling, it still fails because it didn't send the callback. The core reason CloudFormation hangs is the missing S3 callback, not the permission itself. C. Lambda-backed custom resources do not require the CloudFormation update stack or CloudFormation signal resource permissions. The mechanism relies entirely on the HTTP put to the pre-signed S3 URL. D. Exiting cleanly with a zero status code indicates to the Lambda runtime that the invocation succeeded. However, CloudFormation does not monitor the Lambda runtime exit codes. It strictly monitors the S3 callback URL. A helpful shortcut is this. If a CloudFormation stack hangs on a custom resource and eventually times out, the backend Lambda function failed to send the required JSON response object back to the provided pre-signed S3 response URL. Question number 120. Let's go. Scenario. A software development team uses AWS CodeCommit to host their Git repositories. The team practices a feature branch workflow where developers commit code to individual feature branches and merge them into the main branch strictly via approved pull requests. Currently, all developers have the AWS Managed Policy AWS CodeCommit Power User attached to their IAM roles. However, the DevOps lead discovers that several developers are bypassing the pull request process and pushing commits directly to the main branch. How can the DevOps lead restrict developers from pushing directly to the main branch without disrupting their ability to push to feature branches? Choices. Option A. Remove the AWS CodeCommit Power User Managed Policy from the developers. Attach the AWS CodeCommit read-only managed policy along with a custom policy granting Git push and put file specifically with a condition restricted to the main branch. Option B. Modify the existing AWS code commit power user managed policy to insert a deny statement for the code commit. Git push and code commit. Put file actions targeting the specific repository with a condition matching the main branch reference. Option C. Attach a customer-managed IAM policy that explicitly denies code commit. Git push and code commit. Put file on the protected repositories when code commit. References is refs/heads/main. Use string equals if exists for code commit. References, and include a null condition requiring code commit. References to be present, then attach the policy to the developer's roles. Option D. Create a new custom IAM policy containing an allow statement for the code commit. Git push and code commit. Put file actions. Scope the statement to the specific repositories and include a string equals condition for code commit. References matching refs/heads/feature/star. Attach this new policy to the developer's IAM roles. Go with option C. Attach a customer-managed IAM policy that explicitly denies code commit. Git push and code commit. Put file on the protected repositories when code commit. References is refs/heads/main. Use string equals if exists for code commit. References, and include a null condition requiring code commit. References to be present, then attach the policy to the developer's roles. Let's look at the reasoning. An explicit IAM deny overrides the broad allow in AWS code commit power user, so a targeted deny can protect main while leaving feature branch permissions intact. For a policy that denies git push based on code commit, references, AWS code commit guidance uses string equals if exists together with a null condition that requires the reference's context key to be present. Omitting that safeguard can break git push processing rather than only blocking the protected branch. The other choices do not work because A. Removing the power user policy and attempting to explicitly allow every possible code commit action, read, write, PR creation, branch management, across all repositories using a custom policy is a massive administrative burden. Adding a targeted deny policy is far more efficient. B. AWS managed policies, like AWS code commit power user, are maintained by AWS and cannot be directly edited or modified by customers. You cannot insert a deny statement into it. D. Creating an allow statement restricted to feature branches does not solve the problem because the developers already possess the broad AWS code commit power user managed policy, which grants them allow access to the entire repository. The explicit deny is required to override the existing allow. The main takeaway is to protect a code commit branch with IAM. Use an explicit deny scoped by code commit. References, and include the required null condition when git push is part of the deny statement. Next, question number 121. Next, let's move into disaster recovery. A global enterprise operates an e-commerce platform using Amazon EC2 instances in an auto-scaling group behind an application load balancer. ALB. The platform's backend database is an Amazon RDS for PostgreSQL instance. Amazon Route 53 is used for DNS routing. A newly updated business continuity policy requires a geographically isolated disaster recovery site. The business mandates a recovery time objective, RTO, of 2 hours and a recovery point objective, RPO, of 5 minutes. The DevOps team must implement a solution that requires the least amount of architectural redesign to the application layer. Which disaster recovery strategy will satisfy these constraints? Option A. Deploy a mirrored application stack in a different availability zone within the same AWS region. Create an RDS red replica in the new availability zone. Use a Route 53 failover routing policy to redirect traffic if the primary stack fails. Option B. Deploy a mirrored application stack, excluding the database, in a different AWS region. Take frequent automated RDS snapshots and copy them to the disaster recovery region. In the event of a failure, restore the latest snapshot and update Route 53 to point to the disaster recovery ALB. Option C. Deploy a mirrored application stack, excluding the database, in a different AWS region. Create a cross-region RDS red replica in the disaster recovery region. Configure the disaster recovery application stack to use the local read replica. Use a Route 53 failover routing policy and promote the read replica to a standalone primary database during a failover event. Option D. Deploy a mirrored application stack in a different AWS region. Create a cross-region RDS read replica. Use a Route 53 latency routing policy to balance traffic between the regions. Promote the read replica to primary in the event of an outage. The best choice is option C. Deploy a mirrored application stack, excluding the database, in a different AWS region. Create a cross-region RDS read replica in the disaster recovery region. Configure the disaster recovery application stack to use the local read replica. Use a Route 53 failover routing policy, and promote the read replica to a standalone primary database during a failover event. This works because this architecture represents a warm standby, or pilot-light, disaster recovery pattern across regions. A cross-region RDS read replica utilizes asynchronous replication, easily meeting the 5-minute RPO requirement. By having the infrastructure, ALB, EC2 ASG, pre-provisioned in the disaster recovery region and Route 53 failover routing configured, the RTO of 2 hours can easily be met by simply promoting the database and letting the ASG scale out if necessary. This requires minimal application changes. The remaining options can be eliminated because A. Deploying in a different availability zone does not provide a geographically isolated disaster recovery site, region-level disaster recovery. B. Relying on automated snapshot copy and manual restoration will likely exceed a 5-minute RPO because snapshots are point in time and copying takes time. Continuous replication is required for strict RPOs. D. Latency routing is designed for active-active architectures to route users to the region with the lowest latency. A disaster recovery scenario typically uses failover routing to route all traffic to the secondary site only when the primary site fails. Here's a useful exam tip. For strict cross-region database RPO requirements, minutes, rely on cross-region read replicas or global databases rather than snapshot copies. Now for question number 122. Here's what is happening. A company is developing a fleet management application running on Amazon EC2 instances within an auto-scaling group. The instances receive traffic from an application load balancer. The application connects to an Amazon RDS from MySQL database to read and write fleet telemetry. The company maintains separate staging and production environments. A DevOps engineer needs to determine how the application should authenticate with the database without hard-coding sensitive information into the source code or build artifacts. What is the most secure and flexible method for passing the database credentials to the application instances? The choices are: Choice A. Attach an IAM role to the EC2 instances. Store the database credentials in AWS Secrets Manager and allow the application to dynamically retrieve the credentials at runtime using the AWS SDK. Choice B. Retrieve AWS access keys and the database credentials from AWS Systems Manager Parameter Store secure string parameters during the application startup script. Choice C. Attach an IAM role to the EC2 instances. Encrypt the database credentials in a configuration file using AWS KMS. Bundle the file with the application code and decrypt it locally on the instance. Choice D. Store the database credentials as plaintext parameters in AWS Systems Manager Parameter Store. Allow the application to retrieve them at runtime using an IAM user's long-lived access keys. The right response is option A. Attach an IAM role to the EC2 instances. Store the database credentials in AWS Secrets Manager and allow the application to dynamically retrieve the credentials at runtime using the AWS SDK. Here's why. AWS Secrets Manager is the optimal service for storing, rotating, and managing database credentials securely. Using an IAM role attached to the EC2 instance, an instance profile, adheres to the principle of least privilege and avoids the need to distribute or hardcode static AWS credentials. B. While parameter store secure string is valid for secrets, providing AWS access keys via the parameter store completely defeats the purpose of IAM instance profiles and introduces severe security risks. C. Encrypting credentials in a configuration file makes credential rotation extremely difficult and tightly couples the secret to the deployment lifecycle, lacking flexibility. D. Plaintext parameters expose sensitive data, and long-lived access keys are an anti-pattern for EC2 instances. Exam tip. Always use IAM roles, instance profiles, for compute resources, EC2, ECS, Lambda, instead of distributing static IAM access keys. Question number 123. Let's go. This question takes us into organizations and SCPs. Scenario. A technology company manages dozens of AWS accounts using AWS organizations. Each engineering team has its own AWS account and requires full administrative rights within that account to manage their workloads independently. However, the company's security baseline dictates that teams may only consume AWS services that have been formally reviewed and approved by the Central Architecture Board. How should a DevOps engineer enforce this service restriction while maintaining the developer's administrative permissions? Options. Option A. Use AWS Cloud Formation Stack sets to deploy custom IAM policies to all member accounts that explicitly deny access to unapproved services. Attach these policies to all IAM users and roles in the accounts. Option B. Place the engineering team's accounts under a dedicated organizational unit, OU. Create a service control policy, SCP, that uses a deny effect with a not action condition specifying the approved AWS services. Attach the SCP to the OU. Option C. Implement an AWS config rule in each member account that monitors the usage of unapproved services. Configure a remediation action using AWS Systems Manager to automatically delete non-compliant resources. Option D. Configure AWS IAM Identity Center, AWS Single Sign-On, in the management account. Provision permission sets with administrator access, but add inline policies that deny access to restricted services. In this case, choose option B. Place the engineering team's accounts under a dedicated organizational unit, OU. Create a service control policy, SCP, that uses a deny effect with a not action condition specifying the approved AWS services. Attach the SCP to the OU. The main reason is service control policies, SCPs, act as a maximum permissions guardrail for an entire AWS account or organizational unit. Even if a developer is granted administrator access via IAM policies, they cannot bypass an SCP. Using effect, deny with not action efficiently creates an allow list. It denies all actions except the ones explicitly listed as approved, scaling perfectly without needing to list every single restricted service. Let's quickly check the incorrect choices. A. IAM policies deployed via stack sets can simply be detached or modified by a user holding administrator access, defeating the restriction. C. AWS config provides reactive detection and remediation, but the requirement is to strictly enforce service restriction, preventative control. D. IAM Identity Center inline policies restrict human federated access, but developers could still create local IAM users or roles with elevated permissions to bypass the restriction. Keep this point in mind for the exam. SCPs override all local IAM permissions. To mandate boundaries for administrators, SCPs are the only robust preventative control. Next up is question number 124. Here's the scenario. A media streaming service generates high volumes of application logs that are sent to Amazon CloudWatch logs. The analytics team frequently queries these logs for the first 30 days to troubleshoot user experience issues. After 30 days, the logs are rarely accessed but must be retained for 7 years to meet data retention compliance laws. The company wants to archive these logs into an Amazon S3 bucket to optimize costs. Which combination of steps should a DevOps engineer implement to achieve this? Choose 2. Identify all valid responses. Review the options. Choice A. Configure an AWS Lambda function to run on a schedule to query CloudWatch logs insights and export the results to an S3 bucket. Choice B. Configure a CloudWatch log subscription filter to stream all incoming log events into Amazon Kinesis Data Firehose, which is configured to deliver the data to the S3 bucket. Choice C. Create an S3 lifecycle policy to transition the archived logs to S3 Glacier flexible retrieval after 30 days and permanently delete the objects after 2,555 days. Choice D. Configure a CloudWatch log subscription filter to stream all log data directly into the Amazon S3 bucket without requiring intermediary services. Choice E. Create an S3 lifecycle policy to transition the logs to S3 standard and frequent access after 7 years. The answers that work here are option B. Configure a CloudWatch log subscription filter to stream all incoming log events into Amazon Kinesis Data Firehose, which is configured to deliver the data to the S3 bucket, and option C, create an S3 lifecycle policy to transition the archive logs to S3 Glacier flexible retrieval after 30 days, and permanently delete the objects after 2,555 days. This is the best choice because CloudWatch logs cannot stream directly to S3 natively. It requires an intermediary. Amazon Kinesis Data Firehose is a fully managed service that natively integrates with CloudWatch log subscription filters to stream log data continuously to Amazon S3. Once in S3, lifecycle policies automate the transition to cost-effective storage, Glacier, when logs are rarely accessed after 30 days, and handle expiration after 7 years per 2,555 days. Here's why the alternatives are not suitable. A Lambda querying CloudWatch logs insights on a schedule is not a reliable or scalable way to stream all logs and may hit API throttling limits or timeout. D. CloudWatch log subscription filters cannot target an S3 bucket directly without a service like Kinesis Data Firehose or Lambda in between. E. S3 standard IA is more expensive than Glacier for long-term archival, and transitioning after 7 years misses the requirement to archive when logs become rarely accessed after 30 days. To export CloudWatch logs to S3 in near real-time continuously, use a subscription filter targeting Amazon Kinesis Data Firehose. Next, question number 125. Scenario. A company's serverless application consists of Amazon API Gateway and AWS Lambda functions. The deployment process must be automated using a CI/CD pipeline. The engineering team requires a canary deployment strategy that shifts 10% of production traffic to the new Lambda function version for 5 minutes before shifting the remaining traffic. If the new version exhibits high error rates during the canary period, the deployment must automatically roll back. Which combination of actions should the DevOps team take to build this deployment pipeline? Choose 3. More than one answer may be correct. Option A. Define the application infrastructure using an AWS serverless application model, AWS SAM, template. Specify the deployment preference type as canary 10% 5 minutes and configure the alarms property for the Lambda functions. Option B. Define the application using standard AWS CloudFormation. Use the AWS Lambda alias resource and manually configure Route 53 weighted records to shift 10% of the traffic. Option C. Create an AWS code pipeline workflow. Add an AWS code build stage to package the AWS SAM template and deploy the resulting artifacts directly using code build commands. Option D. Create an AWS code pipeline workflow. Add a source stage that triggers on code commits, followed by an AWS CloudFormation deploy action to execute the packaged AWS SAM template change set. E. Create Amazon CloudWatch alarms for the Lambda functions configured to trigger if the error's metric exceeds the acceptable threshold. Ensure these alarms are referenced in the deployment configuration. F. Create an Amazon Event Bridge rule that monitors CloudTrail for Lambda update events and triggers an AWS step functions workflow to execute the rollback. You should choose option A. Define the application infrastructure using an AWS serverless application model, AWS SAM, template. Specify the deployment preference type as canary 10% 5 minutes and configure the alarms property for the Lambda functions. Option C. Create an AWS code pipeline workflow. Add an AWS code build stage to package the AWS SAM template and deploy the resulting artifacts directly using code build commands. And option E. Create Amazon CloudWatch alarms for the Lambda functions configured to trigger if the error's metric exceeds the acceptable threshold. Ensure these alarms are referenced in the deployment configuration. AWS SAM natively integrates with AWS Code Deploy to orchestrate safe deployments. By setting deployment preference to canary 10% 5 minutes, SAM provisions Code Deploy to shift 10% of traffic, wait 5 minutes, and then complete. Code Deploy requires CloudWatch alarms specified in the SAM template to monitor the health of the deployment. If the alarm triggers, Code Deploy automatically rolls back the alias routing to the previous version. Code Pipeline orchestrates this flow using code build or CloudFormation deploy actions. Now let's rule out the other options. B. Manual weighted Route 53 records do not provide automated CI/CD canary deployments or automated application-level rollbacks. D. While CloudFormation deploy actions can process SAM templates, The specific combination of A, C, and E accurately describes the necessary AWS SAM syntax, alarming structure, and CI/CD integration. Note: standard SAM CLI commands in code build are very common for deploying SAM. F. Event bridge and step functions are unnecessary custom overhead. Code deploy natively handles rollbacks when integrated with SAM and CloudWatch alarms. A helpful shortcut is this: AWS SAM deployment preference, for example, Canary 10% 5 minutes, relies on code deploy under the hood and requires associated CloudWatch alarms to trigger automatic rollbacks. You have completed Set 7 of the DOP-C02, AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.